All right, so I like to review this great book. This is the second book of Gabriele Eichfelder, and because it is one of the greatest books on multi-objective optimization, and it has a rather general approach to multi-objective optimization, and it includes many different classical algorithm for multi-objective optimization. This book. So I explain this book in seven parts. And although it is just 10 chapters, but I review it in 7 different parts. So as you know, it starts with lexicographical order. We need an order because otherwise we cannot say that which point is better than the other point, because we are living in a multi-objective world that we have many solutions and we have Pareto optimality and all of them. So when we talk about order, we need some cones. So we cannot so relations which are not defined by one single convex cone, but by a family of convex cones, one for each element, are denoted as variable ordering structures. In the last book of Gabriele Eichfelder, she talked about a cone that K is fixed, and in postulated Serafini, so we change A and the direction to minimize T, and that in that case K was fixed. Okay, but in this book that is much more general, we assume that it is not only it is not fixed, but we define a set valued map. It means for any y we have a different cone. So that's why we define the cone by y. So so the map for each point in our objective space, for example, in a 2-dimensional objective space, we have, for each point you imagine, we have a cone. And for any point you imagine, we have a different cone. And of course, we can talk about intersection of all these cones. We call it K, which is constant. So because we are talking about set valued map, it means that for any point we have a cone. We don't have a fixed objects, but also we have a kind of variable ordering, and so it should have some, in a scalar world, we only, for example, we say 3 is greater than 2, but here for all coordinates of that we have to define such a order. And you will see that, for example, you will see that how we define these orders. And if K is called pointed if intersection of K with minus K is 0. And this is the definition of the cone, but it cannot be convex, it can be convex, so we don't know. And so the cone of a set is we try to, for example, we have a set here. We try to find the minimum cone that we can make, and that's why it is we are trying to make a cone from any kind of set. And the convex cone, the convex hull of a set, it means we have a set of points. We want to find the minimum convex set that we can make from that. And a cone is convex if and only if. So this is the definition for a convex cone. And we have a theorem that says that if this is a partial ordering, then the set is a convex cone. These are very simple theorems, and this is just an example of cone. But in the previous book of Eichfelder, we were talking about a very simple cone and usually just simple trivial cone. And the dual cone is we are trying to make some objects. For example, if the inner product, when you want to describe this relationship, you say that the inner product of two vectors is positive. Of course, we have a different, when the inner product is negative, it means y prime, y star minus y is less than 0. We are, this is another object which we will call it normal cone, which I will talk about it in lecture 7. But this is lecture 1. We only talk about dual cone. So dual cone with the inner product is positive. The inner product of elements of K, all of them are. This is the dual cone of that. So dual cone has a good property that it is a convex. Although K could not be a convex, but dual cone is convex. And so this is the definition of a dual cone. You can also think about it as a dual space in functional analysis. For example, we have a function space here, function space, and we have a dual space. I mean, the space of all functionals acting on sets, functionals. So this is the dual space. This is the original space, and that is the dual space, because we take advantage of the duality theorems and make it easier to deal with, because they can be mathematically well understood. So we define the core of this is the algebraic interior core. Of course, it is the same as interior of core. If it is a convex set, then both of them coincides because they are the same things. But if it is not a convex set, then we have to define such a set. So we try to generalize the concept of interior of a set. And we have a theorem that this relation holds, and we can say that if Y is locally convex, then K is closed. The concept of closed is different from boundedness. It could be closed and not bounded. These are concepts from topology. And also we can define some some binary relationship, some define a variable ordering like this. So Y matters, for example, Z matters. For example, if both of them satisfies, then that would be a constant cone. And we have some easy lemma for the properties of these cones. For example, when I say we are generalizing the constant cone, that we talked about it in the previous book of Eichfelder, for each point we have a different cone. So that's why we can often talk about intersection of all cones. Intersection of all cones, which could be K. And it has good properties, and it is convex and many other properties. And that's why I talked about Pascoaletti-Serafini in my lectures on multifactor investing, that Pascoaletti-Serafini didn't talk about it, didn't look at it as a functional. You cannot talk about this easily. But if you define a functional such as psi of y, which is infimum of all t, such that a plus tr minus f of x is inside that cone, then this is a functional. We can define it, and you can talk about smoothness, differentiability of that, even discontinuity of that, and all of that. So you know how it is related to Pascoaletti-Serafini. And we now talk about dominated versus non-dominated elements. For example, this is a cone, and this is a y. This is a simple cone, for example, typical Rm plus cone. And y plus dy, this is y plus dy, is they are considered to be worse than the element y. And that is why we say y is dominated. But look at here. We are saying the opposite thing. Now y is here. Now y minus dy is here and are considered to be better than the elementary y. So y, we cannot say it is non-dominated. It is dominated by many points. And we can define many cones structurally we can define many cones. If we just use the Bishop-Phelps cones, we say BP cones. And all points, when we want to define a cone, such as this cone, for example, we say that this is the space of all points where the norm of y, the Euclidean norm of y, is less than another, the functional in that case. That functional could be L transpose y, where L is a vector and y is a vector, so the dot product is a scalar, which I say that phi is a functional. So we can use measure theory, all different things in functional analysis, because we have encoded all the things that we need for defining a cone. So this is the cone that we have defined, and it is called representable. So if you give me any cone, okay, I can say that I can represent it. I can represent it with BP cones. There exists one phi, there exists a functional such that all the points in the cones could be represented by this one. And of course, there is a theorem that says Vx is closed and convex. This is a really important property. And you can find the interior of this BP cone very easily, because I said that you only need to say that this is the points that satisfies this relationship. So if you just remove the equality, there is no equality here. So then this is the interior. So you can easily find the interior of your BP cone. And a non-trivial cone is representable if and only if K is convex cone with a closed and bounded base. And also we can generalize that if we bring alpha as well. In the original BP cones, phi of y is greater than norm of y. We don't talk about alpha. Alpha is 1. But we can also generalize it, and that's why we define the concept of augmented dual cone. And so we have a definition. K is said to be supernormal if this satisfies. And so this lemma says that it is equivalent to say that it is representable as a BP cone or it is a supernormal. And a simple example of L that is used throughout this book, because it's very easy, is using this kind of functional. L, this is the phi that I was talking about. This is a functional. You give them a point or a vector, it gives you a scalar. And so if we can use this L, but you can use any functional. As long as you can define by BP cones, because it is a quite general class of functionals. Quite a general class of cones that you can represent it by those BP cones.